In the previous videos, I have already given a very brief illustration on how to draw the Bode diagram of complex systems if we know the Bode diagrams of some simpler systems. If we are going to plot it with the help of computer, then it will be easy. You can simply use an Excel or any other computing applications like MATLAB or Python. You can start to plot the Bode diagram of complex systems directly, or you can factorize the transfer function of the complex system into simpler systems, and then summing all of the Bode diagrams of the simpler systems accordingly. But the question now, if we don't have a computer in front of us with an appropriate computing applications, how are we going to plot, or how are we going to sketch the Bode diagram of a complex system? Do we really need to memorize how the shapes are look like for Bode diagrams of simpler systems? The answer is no. There is a logical way to sketch Bode diagram of simpler systems. This is something that we are going to discuss in this short video. Let's start it first with the simplest dynamic system ever, which is a static system. A static system technically is a system where the transfer function is equal to a constant. Let's call it A now here. So now we have a system where the transfer function GS is equal to A. When we are going to sketch the Bode diagram of a system, then what we have to do, the very first step, we have to substitute j omega to all of the s's in our transfer function. But of course, as we are dealing now with a static system, there is no s in our GS, so the j omega will be just simply again equal to A. And the second step, then we have to find the magnitude of this system. The magnitude of my j omega here, of course, it will be again equal to A, right? The magnitude of a real number is the absolute of the real number itself. But now, once we know the magnitude, we have to present this magnitude in dB scale. So this j omega in dB scale will be just simply equal to dB of A, or it's equal to 20 log A. And the angle, what about the angle? The angle of a complex number is equal to the inverse tangent of the imaginary part divided by real part. And in this case, we don't have imaginary part because this is a static system. The transfer function is equal to a real number, so obviously the angle or the phase will be equal to 0 degree. So from here, we can easily sketch the magnitude plot of the Bode diagram. According to this equation of the magnitude plot, we will have a magnitude equal to 20 log A all over frequency. So this is what we will have for the magnitude plot, a constant of 20 log A for all frequencies. What about the phase? The angle, it will also be the same. The angle will be just simply equal to 0 degree for all over frequency. So the plot will be also simply like this. That is for the first simple system, GS equal A. Now let's move to the second simple system. There is an S in our transfer function now. The second simple system that I want to consider now is an integrator. Integrator means 1 over S. So my transfer function here, we have a dynamic system now. the transfer function is simply equal to gs equal to 1 over s. The next step, as usual, I have to replace all of the s's in my transfer function with j omega. So my j omega will be equal to 1 over j omega. The magnitude of j omega will be simply equal to 1 over omega. In dB scale, as usual, 1 omega will be equal to 20 log 1 over omega, or it will be equal to negative 20 log omega. What about the angle? The phase? The angle of j omega, then it will be equal to, I have inverse of omega here, or sorry, I have inverse of j omega. If I replace the s here with j omega, the angle will be equal to the angle of the numerator, where I have numerator equal to 1. 1 is a constant. The angle of a constant of a real number is equal to 0 minus the angle of the denominator. The denominator now is equal to j omega. So 0 minus, so I simply have minus then here, inverse tangent of the angle of the denominator. But now in the denominator it only contains an imaginary number j omega. So the angle of the denominator, then it will be equal to inverse tangent of the imaginary part of the denominator, which is omega, over the real part of the denominator, which is 0. We don't have real part in the denominator. So we have minus inverse tangent of omega over 0, which is equal to negative 90 degrees. Let's see how the plot will look like. I will start it with the magnitude plot. We have magnitude plot as a function of omega now here, right? But remember, the horizontal axis is a logarithmic of omega. The horizontal axis is the frequency in logarithmic scale. So in this case, negative 20 log omega will have a form of linear function with a gradient of negative 20 dB for 1 decade increment in the frequency. So as you can see here, the slope is negative 20 dB per 1 decade, right? Because it is in logarithmic scale. And this line will definitely cross the origin. The origin is 0 of frequency in logarithmic scale. So 1 in logarithmic scale is equal to 0 and 0 dB. So it crosses 0, 0. What I indicated here is the frequency, but the logarithmic of 1 is equal to 0. So this point is the origin. That is for the magnitude plot. A straight line with a gradient of negative 20 dB per decade crossing the origin. What about the angle, the phase plot? As you can see here from what we have already derived, the angle is equal to negative 90 degrees all over frequencies. So the plot of the phase will be simply like this. Constant of negative 90 degrees all over frequencies. In general here, the Bode diagram of an integrator will look like this, as we have already derived before. We have a linear plot of magnitude here with a gradient of negative 20 dB in every decade of frequency, and the frequency plot, the phase plot, the angle plot itself will be constant of negative 90 degrees for all frequencies. That means from this phase plot, the response will always lag by 90 degrees, right? From the magnitude plot, we can see at low frequency, we will have a very high gain. At high frequency, the gain will be very small. Let's move now to the next simple system. Now I have a double integrator. Why do I call this as a double integrator? Because 1 over s squared basically is two integrators in serial connection, right? So how the both diagrams will look like? Obviously, because now I have double integrators, 1 over s times 1 over s, the magnitude plot will be just a superposition of these two integrators. The magnitude plot will be just simply equal to the superposition of two integrators. For a single integrator, we have already derived it before that the magnitude will be equal to negative 20 log omega. So for double integrator, the magnitude plot will be just simply equal to negative 40 log omega. What about the phase? Again, we have double integrators here. The phase plot will be just a summation of the phase of single integrator. In short, the phase plot will be equal to negative 180 degrees all over frequencies. So the phase plot then, if this gray line is the phase, the both plot, if this gray line here for the first plot is the magnitude of a single integrator, for double integrators it will be just simply like this. It's a linear plot here with a gradient of 40 dB for 1 decade frequency increment. Again, this plot still crosses the origin. What about the phase? Again, for the phase plot, if this gray line is the phase plot of a single integrator, the double integrators, this will be negative 40 dB per decade for the magnitude plot. For the phase plot, again, for double integrators, then the phase plot will be just simply equal to negative 180 degrees all over frequencies. Let's move now to the next simple system. Let's call it as a differentiator, where Gs is equal to S. So technically, differentiator in Laplace domain is just simply equal to the inverse of the integrator, right? Where integrator is equal to 1 over S, differentiator is just simply equal to S. The magnitude for Gs equal to S, of course, it will be simply equal to omega, right? Gj omega, my Gj omega now is equal to J omega, so the magnitude of J omega is obviously equal to omega. What about the magnitude? In dB scale, it will be equal to 20 log omega. And the angle or the phase, the Gj omega is equal to J omega. There is no real number on it, so the angle will be equal to inverse tangent of the imaginary part, which is omega, right? The imaginary part of J omega is omega. There is no real part. It will be equal to 0. Inverse tangent of omega over 0, then it will be equal to 90 degrees. How about the both diagrams? Sorry, this is supposed to be Gs equal to S. I made a mistake here. I will make a correction in the lecture note. So this is for Gs equal to S. The magnitude, then it will be equal to 20 log omega. Same like before. Remember the the domain here, the horizontal axis here is omega in logarithmic scale. So obviously the magnitude now will be equal to linear function with a gradient of 20 dB for 1 decade frequency increment, right? Pretty similar like before. What about the phase plot? The phase plot, it is just simply equal to positive 90 degrees for any frequencies. If you compare this plot of this differentiator to the integrator, what do we see? As the differentiator basically is just the inverse of the integrator, what do we see? The Bode diagram of differentiator is also just the inverse of the Bode diagram of the integrator. As you can see here, the magnitude plot is just the mirror plot of the integrator magnitude in horizontal scale. If you compare to the magnitude plot of the integrator, this looks pretty similar. It is only mirrored by the horizontal axis. The same thing for the phase plot. If you still remember, the phase plot of the integrator is equal to negative 90 degrees for all frequency. If you mirror it to the horizontal axis, then the phase plot will be equal to positive 90 degrees for all frequencies. So these are the two Bode plots for differentiator. Now let's move to slightly more complex system. It's still considered to be a simple system anyhow. We have now a first order system, A over S plus A. This means this GS has one pole at negative A. Let's consider A is a positive number now. Before we move to the discussion on how the Bode diagram will look like, I need to mention that A here, the pole, well, the pole is negative A, of course. A is the negative of the pole. A here is what we call as a corner frequency. So whenever you have a first order dynamic system, a stable system, then negative of the pole is the corner frequency of that first order system. Now let's move to the Bode diagram sketching. We have to derive first the magnitude equation. Again, same like before, I have to replace all of the s's in my GS to come up with the GJ omega. I only have one s in my GS here. So the GJ omega, then it will be equal to A over J omega plus A. The magnitude, if you evaluate it accordingly, in dB scale, it will be equal to 20 log A minus 10 log omega square plus A square. How do I come up with 10 log omega square plus A square? It's because the magnitude, the denominator of the magnitude will be equal to square root of J omega, sorry, the denominator of the magnitude will be equal to the square root of omega square plus A square. If I put it in dB scale, then 20 log of square root of omega square plus A square will be equal to 10 log omega square plus A square. You still remember, I believe, on how the logarithmic operation works. Okay, let's go back to this. The magnitude is equal to 20 log A minus 10 log omega square plus A square. How do we sketch the magnitude then from this point? I will analyze it for two different regions. I will first consider how the magnitude will look like at very low frequency. If frequency is very low, close to zero, then my magnitude here in dB scale will be close to 20 log A minus 10 log A square. Remember, the omega will be very small. 10 log A square is equal to 20 log A, right? So in this case, when omega is very, very small, the magnitude in dB scale will tend to be equal to 0. What will happen when omega is very, very, very large? If omega is very large, A square is nothing compared to omega square, right? Let's consider omega equal to 1000. A is equal to 1. 1000 square plus 1 is almost equal to 1000 square. So when omega is very, very, very large, I can neglect the A square part. At the end, the magnitude when omega is very large is equal to 20 log A minus 10 log omega square. 10 log omega square will be equal to 20 log omega. So this what the magnitude plot will look like when omega is very, very, very large. Now, how the sketch will look like then. When omega is very small, I will sketch it that the magnitude plot will be equal to 0 for low frequency until, let's say, until it arrives at the corner frequency. Beyond the corner frequency, I will consider that region as a large frequency region. So beyond this corner frequency, I will consider the plot following the second approach here. The plot beyond this corner frequency will be equal to 20 log A minus 20 log omega. This means then, if you look at the second term here, I will have a line with the gradient equal to negative 20 dB per decade beyond the corner frequency. So after this corner frequency, the rough sketching of this magnitude will look like this, where the slope here is equal to negative 20 dB per decade. Now this is what the straight line sketch, the rough straight line sketching of the magnitude of this first order system will look like. What about the phase? What about the angle? Same like before. The angle then it will be equal to, after I replace the S here with j omega, the angle will be equal to the angle of the numerator minus the angle of the denominator. The numerator only contains real number, so the angle of the numerator will be equal to 0 minus the angle of the denominator. The denominator contains j omega plus a. The imaginary part is omega, the real part is a. So the angle for this j omega will be equal to minus inverse tangent omega over a. How to plot it? I will do the same thing. When omega is very small, then the angle will be equal to 0, right? When omega is very small, omega is small, then minus inverse tangent of omega over a will tend to be equal to 0. When omega is very large, omega will tend to be a large number, minus inverse tangent of large number will be equal to negative 90 degrees. The straight line sketching of this phase plot, then it will be 0 degrees for low frequency region below the corner frequency of A, and negative 90 degrees at the high frequency region above the corner frequency of A. This is how we derive the straight line sketching of the Bode diagram of first order system. I have a few more things to mention about this Bode plot, in particular the phase plot. In real plot, it is not really realistic to have a very sharp jump in the phase plot. This is not wrong. This phase plot is definitely not wrong, but if I want to have a better approximation, to have a very sharp jump like this is not really realistic. So what I'm going to do, normally when I want to derive the phase plot of a first order system like this, what I will do, I will split this region, instead of having only two regions at low frequency region and high frequency region, I will split it into three regions. The first region is the low frequency region, from low frequency until 1 decade below the corner frequency. So from low frequency until 1 decade below the corner frequency, I will consider that region as the low frequency region. So from low frequency until 0.1A, I will have the low frequency phase plot, and beyond 1 decade above the corner frequency, I will consider this region as the high frequency region. So at high frequency region beyond 10A, the frequency will be equal to negative 90 degrees. What about at the middle region then? The region between 0.1A and 10A. You just have simply to connect these 2 points. So I will have a straight line at this middle frequency region with a slope of negative 45 degrees per decade. This comes from because I will have negative 90 degrees jump for 2 decades. So the slope here will be equal to negative 45 degrees per decade. The first approximation is not wrong, but the second approximation of the phase plot will look more realistic, will look closer to the real phase plot. So let's take a look again a bit more detail on the magnitude plot, and then later on the phase plot of this first order system. Let's take a look first on the magnitude plot. As I have already mentioned before, at low frequency regions below the corner frequency, we will have 0 dB for the magnitude, and we will have a straight line with negative 20 dB per decade at high frequency region beyond the corner frequency. But this is only the straight line sketching. How the real plot typically look like? The real plot typically looks like this one, right? If you plot it using Excel or MATLAB or anything, by plotting it frequency by frequency, you might have the plot that looks like this red curve, like what you can see in this slide. Normally, I want to introduce one more terminology here. The frequency at which the magnitude from the real plot here is equal to 3 dB below the magnitude at low frequency. So this one, let's say, so the frequency at this point will be slightly higher than, slightly larger than A. This is what we call as the bandwidth frequency. So this frequency, the frequency at which the magnitude is about 3 dB below the magnitude at low frequency, this frequency is referred to bandwidth frequency. This bandwidth frequency obviously will be slightly larger than the corner frequency A. This is one term that I want to introduce to you from this slide. What about the phase plot? For the phase plot, the gray straight lines here are the straight line sketching of the phase plot. The real phase plot typically will look something like this. So as you can see here, our straight line sketching with considering these three regions, low frequency region, high frequency region, and middle frequency region, looks better to approximate the real phase plot compared to if we only consider two regions with a sharp step in the phase plot. So this is what typically will look like for the phase plot of a first order system. Now let's take a look on the inverse of first order system. So if you look at this again, the equation here is just simply the inverse of the first order system, where GS is equal to S plus A over A. Again, in this case here, A from the finite zero here, the finite zero of this first order system, the inverse of first order system here is equal to negative A. So in this case, A is the corner frequency again. How the both diagram will look like? We can do the same steps like what we did before. Find the magnitude, take the magnitude in dB scale. The magnitude in dB scale will look like this. Analyze the approximation for low frequency region and analyze it also at high frequency region. Do the same thing for the phase. Find the phase equation. Analyze the phase at low frequency region and high frequency region. After you have done it, you can immediately derive that the straight lines sketching for the magnitude of the inverse of the first order system will look like this. It will be equal to 0 at low frequency, below the corner frequency, and above the corner frequency we will have straight line with a increasing line with a gradient equal to positive 20 dB per decade. What about the phase plot? At low frequency, the phase will be equal to 0, while at high frequency region, the angle will be equal to 90 degrees. As an alternative of this phase plot, same like before, I will split it now, the frequency, into three regions. Low frequency region, that is for the frequency before before 1 decade below the corner frequency, and high frequency region are those above 1 decade above the corner frequency. So the straight line sketching of this alternative phase plot will look like this. The slope at the middle frequency region obviously will be equal to positive 45 degrees per decade. Again, if you compare these plots to the plots of the both diagram of the original first order system, where we discussed it already in the previous two slides, where GS is equal to A over S plus A, what we can see? the magnitude plot as well as the phase plot, both of them are just mirrored by the horizontal axis. Okay, so if you know how to derive the both plots of the typical first order system that we have already discussed in the previous slide, you should be able to derive also the inverse of the first order system both plots. So same like before, let's take a look again how the typical both plot of the inverse of first order system will look like. What we can see here in this slide is the straight line sketching of the magnitude, and the real magnitude plot typically looks like this. Obviously, when the similar to what we have already discussed before, when the magnitude now is slightly greater than 0 dB, when the magnitude is equal to 3 dB above 0 dB, then at that frequency, that is what we call as a bandwidth frequency. While for phase plot, the typical phase plot for the inverse of first order system will look like this. Same conclusion like what we have discussed before. The three region straight line approximation looks to resemble more than if we use only the two region straight line sketching for the phase plot. Let's move now into slightly even more complex system, second order system. Exactly, I will take exactly the same steps like what we did before, but for second order system, the corner frequency is the omega n. Okay, this is something that you have to make sure you know this exactly. For second order system, the corner frequency is the omega n in our second order system. Now we are ready to sketch the magnitude and the phase plots accordingly. Same like before, derive the GJ omega by replacing all of the s's with j omega, take the magnitude and then present it in dB scale. If you have done it, then this will be the magnitude in dB scale. You have to analyze how the magnitude will look like at low frequency. When omega is very small, then obviously this will be nothing. You can consider this equal to 0. This will also be equal to 0. 0 times 2 zeta omega n will be 0. So you will end up into 40 log omega n minus 10 log omega n power of 4. 10 log omega n power of 4 is equal to 40 log omega n. So this will become 0 for low frequency region. What about at high frequency region? Omega will be very large. If omega is very large, then omega n means nothing to omega. I can neglect this part, so the first term here will become omega power of 4. Well, this term I will have 2 zeta omega and omega square. Omega square means also nothing to omega power of 4 if omega is very large. So I can also neglect this part. At the end, I will only end up into 40 log omega n minus 10 log omega power of 4. Or I can rewrite it into 40 log omega n minus 40 log omega, right? Now we can start to sketch the magnitude plot. Same like before, at low frequency region below the corner frequency omega n, the magnitude will be equal to 0 dB, while at high frequency region above the corner frequency omega n, I will have a straight line with a gradient with a slope equal to negative 40 dB per decade. This will be the straight line sketching of this second order system. What about the phase plot? It is the same like before. We just have to derive the phase equation, as you can see in this slide, and then we analyze it at low frequency. Omega is 0. 0 divided by omega n squared, it will be 0. Inverse tangent of 0, it will be 0 degree. And at high frequency, we also have to analyze it. Omega divided by minus omega squared, obviously because this will be large, but then this will be 0 minus large, very, very large number, right? So omega n squared means nothing to omega squared. But look at it now. Omega, we have 2 zeta omega and omega divided by minus omega squared. I can neglect omega n squared, as I have already mentioned before. So I have 2 zeta omega and omega divided by minus omega squared. Then omega means nothing to minus omega squared. At the end, I will get negative 180 degrees. Something divided by a very large number, then it tends to be 0. Inverse tangent of minus inverse tangent of 0, then it will be equal to minus 180 degrees. But why isn't it 0 then? Inverse tangent of 0 can be also 0, right? Why did I choose negative 180 degrees? Why not 0 degree? It's because the negative sign in the denominator, right? Because of this negative sign, as I have already mentioned before, when omega is very large, then this will tend to be small compared to the denominator, and the denominator is considered, it can be considered as minus omega squared, because omega n squared is nothing compared to omega squared. So at the end, at the denominator, I have a negative sign. So small number divided by negative large number. Because of this negative sign, even though this value will be equal to 0, the inverse tangent of this 0 will fall in the other quadrant, right? In quadrant 3 and 4. It's not at the quadrant 0 and 1 because of this negative sign at the denominator. That's why the angle here, I chose it as negative 180 degrees instead of 0 degree. So how the phase plot will look like? At low frequency, it will be equal to 0 degree. At high frequency, it will be equal to negative 180 degrees. But again, as before, as an alternative, I can also sketch the phase plot as what we agreed before. I split it into 3 regions. At low frequency region, it will be 0 degree. At high frequency regions, it will be negative 180 degrees. And what is in between, I just connect these 2 points. But because I have a drop of negative 180 degrees, obviously this slope now will become negative 90 degrees per decade. Let's take a deeper look on how the typical second order system Bode diagram will look like. The gray plot here is the straight line sketching that we have already derived before. The real plot might look like this. For different zeta, you might have different magnitude plot. So what I drew here with a red color here is the magnitude plot of second order system when zeta is equal to 0.9. For different zeta, the real plot will be different. This is what we typically have when zeta is equal to 0.7. It will be closer to the straight line sketching. But when zeta is very small, then we will have a peak in that corner frequency. As you can see here, the smaller the zeta, the higher the peak that we will have at the corner frequency. At zeta greater than 0.7, typically we don't really see peak at the corner frequency. What about the phase plot? So the gray plot here is the gray line here is the straight line sketching of the phase plot, and the typical phase plot for this second order system might look like this for zeta equal to 0.9. For zeta equal to smaller number, it will become sharper and sharper around the corner frequency. So probably for very low zeta, the two region straight line sketching for the phase plot might resemble better compared to the real phase plot. What about the second order inverse? I think if you want to derive it step by step, you can just follow what we have gone through before, deriving the magnitude equation, analyze it for low frequency and for high frequency. Again, same thing, you have to do it for the phase plot, derive the equation, analyze it for low frequency at high frequency, and then after that you have to sketch it accordingly. But from the lesson that we have already learned before, that the inverse of the transfer function, the both plots will just simply the mirror of the both plot of the function itself. So in this case, then the both plots of a second order inverse will be mirrored by the horizontal axis from the both plots of the second order system. So these both plots, I just derive it directly by mirroring the both plots that we have obtained in the previous slide. As you can see here, we will have 0 dB at low frequency for the magnitude plot, and then I will have an increasing line at the gradient of 40 dB per decade after the corner frequency, while the phase plot will be like this. At low frequency we will have 0 degree, at high frequency we will have 180 degrees. Accordingly, if we use the three region sketching for the phase plot, we will have increasing line at positive 90 degrees per decade in the middle frequency region. Okay, so as a summary then, these next three slides I summarize the both diagrams for different simple systems. The first one is the both diagrams for a constant function, or basically this is a static system. Constant magnitude all over frequency, constant phase at 0 degrees all over frequency. The second one, the second row here, is the magnitude and phase plots for differentiator system, and the third one is for integrator. The second page of this summary is for the second for the first order system and also for its inverse. 0 dB at low frequency, negative 20 dB per decade at high frequency for the ordinary first order system, and the phase plot, as you can see in the next column here. Accordingly, the last line here is for the inverse of the first order system. As you can see, the magnitude plot as well as the phase plot is just the mirror of the first order system, the original first order system, mirrored at the horizontal axis, right? The next slide is for the second order system. So we have already discussed it also. We have 0 dB for the magnitude plot at low frequency, a line of negative 40 dB per decade at high frequency, and the phase plot will look like this, where at the middle frequency region, the slope will be equal to negative 90 degrees per decade if you take the 3 region straight line sketching phase plot. Accordingly, the inverse of first order system, the magnitude and the phase plots will be just the mirror of those plots in the original second order system. Okay, so once you know how to sketch these simple systems, at least these 7 simple systems, you will be able to sketch any complex system.